Thanks for your question on Taylor series. I have included a formula for a general Taylor series next to the star that I just put in here. If you have trouble remembering this formula, or if you want a reason for like where the formula is coming from, which actually is how I remember it, is not by memorizing it, but understanding the structure behind it, stick around to the end of the video. I'll include a section on that here. But if you've already got the formula down, or if you don't really care, you just want to hear how to use it, cool, let's jump right in. So your particular question was given the function f of x equals 1 times x, which if I'm going to be so bold as to note that 1 times anything is just equal to itself. So I'm going to go ahead and just call this f of x equals x. Given that function, you're looking for the Taylor series centered at an x value of 6, which we sometimes write as at c equals 6. All right. In general, when finding Taylor series, we're going to want to take a bunch of derivatives. You can see that from the formula already, right? We've got the original function evaluated at c, and then we've got its derivative, its second derivative, and in general, this formula here, this little power in parentheses doesn't mean that I'm raising f to a power. It means when I've got the little parentheses there that I'm taking the nth derivative. So that is the general term of this sum, and that's the sort of thing that, like, if we got rid of the plus signs and the dot dot dots here, I could use that to write the general summation notation. I've put the giant sigma there and say that I'm going from n equals 0 all the way to infinity. That bottom line there is how I could write the general series. But for now, we're just trying to organize our work to be able to take that series. So let's go ahead and take a few derivatives. I always like to kind of write this part out to get myself organized. And sometimes you can even write the second part out too, because eventually we are going to want to take not just the series of derivatives, but evaluate each of them at c in order to plug into the formula. If you can find a pattern, sometimes that makes it really easy to find the general term. So let's jump right in. We're given the first value, the first function really, f of x is equal to x. And so if I'm evaluating that at f of c, well, c is 6. If f of x is x, f of 6 is 6. Not too hard so far, huh? All right, now I want to take the derivative of f of x. The derivative of x is just 1. Still pretty friendly so far. Well, if f prime of x is 1 everywhere, then f prime of 6 is again 1. Hooray! Cool. Even easier from here, if I'm now taking the second derivative of my original f, this one here, the second derivative of x is the first derivative of that thing that I just took. So the derivative of 1, derivative of any constant is 0. So in fact, I can actually continue the pattern all the way from here. For any n value equal to 2 or greater, the derivative of 0 is still going to be 0. So I can just say this is 0. Mathematicians will sometimes use this notation, a little upside down a. That means for all n greater than or equal to 2. Well, okay, if my derivative is 0 anywhere, then my derivatives are going to continue being 0 when evaluated at 6 at my center of my Taylor series. Very cool. We've got all of the pieces put together. We can literally just plug into the formula now. Let's get our final answer. These Taylor series of the function f of x equals 1 times x evaluated, centered at x equals 6 is going to be, well, let's look at my first term. It's just going to be f of c. We know that that's 6 now. Plus, my second term is going to have an f prime of c. F prime of c we found was 1. Times the quantity x minus c. Well, I can just write that in. X minus 6. Not so hard. I can continue getting higher and higher powers here. What you're going to notice in these next terms is, okay, the next thing I'm going to have here is going to have this f double prime of c, which is 0. If I take 0 and divide it by 2 and multiply it by anything, I've still got 0. Same deal with the rest of these. If I take anything that's 0 and divide it by some number and multiply it by some number, I'm still going to get 0. So I could write in my final answer here plus 0, plus 0, plus 0. I could even write dot, 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 plus 0, dot, dot, dot. I don't really need to, though. I could just say this is my final answer, which is really nice for the convergence. This is a finite sum. So my series definitely converges everywhere because I can always add up finitely many things. All right, here's where we start to get into the theory of transitioning from this question to the general one. So recognizing that this converges everywhere, let's think about the meta behind this. If I look at this whole formula that we've just concluded with, remembering, okay, this one is going to work everywhere. I don't need any fancy like convergence tests or anything to confirm that. I can just see algebraically, this is always equal to x at any x value, right? I could literally multiply that out and simplify it, and it's just 6 plus x minus 6. That's equal to x. This looks really dumb in this case, but what the Taylor series is useful for is, in general, we are trying to find a formula series, which is going to be a good approximation of my function. It'll be a perfect approximation if I evaluate it across the entire series, but if I truncate that series, if I take some finite chunk of it, in this case, I can take a finite chunk and actually have it be my entire series, so I know I'm good everywhere. But if I've got an infinite series and I take some finite piece of it, if I can get that something that's still a pretty good approximation, but have a function that's much easier to wrangle. So for something like the one we've got here of f of x equals 1 times x, not too bad to wrangle as is. But with something like f of x equals ln of x, or f of x equals secant squared x over x to the third minus ln x, right? Things can start getting messier. If I can make a series, let's look at the pattern of this series. I've got just a constant, and then a constant times x minus c. That's just going to be a linear term. Next piece here is just a constant times a quadratic term. Every piece of this is just a constant times the next power polynomial. You might know at this point from taking all these derivatives and all these integrals, you're probably most excited when the function you're dealing with ends up being with a polynomial, because taking derivatives and taking taking derivatives and taking integrals of polynomials is way easier than a lot of other ones. So this is what Taylor was working with, was trying to see, can I get a polynomial approximation of my original function that I can work with and have an easier time dealing with that and getting better approximations in a time before I had anything like electronic calculators and I had to do out all of the math by hand. Polynomials are much easier to work with in terms of the computational side of it as well. So here's the motivation behind the particular polynomial that he came up with. It's, he was saying, and here I'll actually go to a new board, we'll develop the series together so you can see how nice it is to work with. He was saying, I want a function, gonna name it after myself, Taylor, because I am just such a smarty old math guy. I want a function which is going to match exactly at the point I'm pecking. So let's start by saying, all right, at x equals c, they're going to be exactly equal to each other. All right. Well, if I don't want to mess that up now that I've put it down here, let's use a trick so that every term that I include beyond here is going to cancel out when I plug in x equals c. Well, an easy thing that cancels out when I plug in x equals c is just x minus c, right? At c, x minus c is equal to 0. So whatever coefficient I put in front of here is going to disappear. So you might notice in the generalized formula, I do in fact have x minus c's in every term from here. All right, cool. This is now a function which is good at my point. Let's go a little broader than that. Let's, now that we've got the power of derivatives behind us, make it match at, make the derivative match at x equals c as well. If I plug an f prime of c in as this coefficient, see how this kind of looks like a linearization now? This is almost point slope form, right? I've got my slope, an x minus an x value, plus my y value. This is exactly the linearization of the function. Indeed, if I truncate a Taylor series after the first two terms, it is exactly the linearization of the function. This is always going to be a function that matches at the point x equals c and that has a first derivative that matches. Well, okay, if it has a first derivative that matches, then if I go and take the derivative of this, I should indeed see. Okay, let's actually take it here. If I take t prime, recognizing I'm not done taking the full series yet, but we'll look into that in a sec. Take the derivative of this constant term, it's just 0. Take the derivative of this bit here. I can always carry down scalar, some constant multiple outside, and the derivative of x minus c is just 1. Cool. So this indeed matches at my first derivative. Now, in order to get it to match at my second derivative as well, we can almost sort of like backwards think our way from here. If I want my first derivative to match and I want my second derivative to match, well, why don't I make my second derivative match by modifying this first derivative formula here? If I want this to kind of be like the linearization like we had above, I can have this be f prime of c times f double prime of c times x minus c. But now if I want to go backwards, if I am anti-differentiating, integrating the second term here, the derivative of a quadratic is what gives me a linear component. So in order to get that bit here, I'm going to need to have an x minus c squared. Well, but if I had the squared here and I'm taking the derivative and that 2 is coming down, I don't have a 2 out here in that thing. So I'm going to need a divided by 2 to cancel out with that. And then if I put the f double prime, the second derivative evaluated at c here, then that will work out. And if I keep going from here, I'm going to keep getting these things. When I do the third derivative and I take 3 layers of derivatives of that Taylor polynomial, the 2 is going to come down and the 3 is going to come down. When I take the nth derivative, the n is going to come down and the n minus 1 is going to come down and the n minus 2 is going to come down. That's where that n factorial in the denominator is coming from, is from taking a whole bunch of derivatives and having, by the time I get to the nth derivative of t of x, the only thing that's left is that nth derivative evaluated at c. Oh, come on, you can write an n. I'm having trouble with my pen. There we go. Nth derivative evaluated at c. As I have that x minus c to the n, and I take n derivatives of that, and so that n chips off, and then that n minus 1 chips off, and that n minus 2 chips off, I'm multiplying n times n minus 1 times n minus 2, and canceling those all out, and that gives me my n factorial. And so that's why I've actually never memorized the Taylor series formula, but can still show it to you right now as I'm thinking about the structure of it and the motivation behind it. So if that helps you think about Taylor series at all, then I hope that was useful to you. Please have a great day. Thanks for watching.